Welcome back to G Fun Facts Online, your go-to spot for mind-blowing science and tech. Today, we're diving into something straight out of a sci-fi blockbuster. Imagine this. You're on a crowded train, listening to your favorite tunes, or maybe catching up on this very podcast. But here's the kicker. You're not wearing any headphones, and no one else can hear a thing. Sounds like magic, right? Well, it's not magic, it's science. We're talking about a revolutionary technology called Acoustic Metasurfaces, and they're poised to completely change how we experience sound, creating what some are calling, quote, virtual headphones. For as long as we've had personal audio, we've faced a dilemma. Headphones give you privacy, but they also cut you off from the world. And let's be honest, they can get uncomfortable after a while. On the other hand, loudspeakers share your audio with everyone, which isn't always what you or the people around you want. There have been attempts at directional sound, trying to beam audio to a specific spot, but they often suffer from sound leakage. You still hear whispers of it along the beam's path. The dream has always been to create these little pockets of sound, or audible enclaves, where only you can hear what's playing. Total privacy, no isolation. So what's the secret sauce? Enter acoustic metasurfaces. Now these aren't just bits of plastic or metal, they are super engineered materials. Picture a thin surface covered in tiny, intricate patterns, like little repeating structures, maybe membranes or tiny holes, all much smaller than the wavelength of sound they're designed to play with. Think of them like an advanced lens for sound. But instead of just bending sound, they can sculpt it, twist it, and direct it with incredible precision. They can control the phase, amplitude, and direction of sound waves in ways natural materials just can't. This opens up a whole new world of acoustic possibilities, like beaming sound with pinpoint accuracy, focusing it, or even creating complex sound patterns in midair. One of the coolest tricks these metasurfaces can pull off is creating those audible enclaves we talked about. It's pretty ingenious. Here's a simplified version of how it works, using something called difference frequency wave generation. First, two separate ultrasonic beams are shot out. Ultrasound is sound with frequencies way above what we humans can hear. Think dog whistles, but even higher. So these beams travel silently. These silent ultrasonic beams are then passed through our specially designed acoustic metasurfaces. The metasurfaces work their magic, precisely controlling the phase of these waves, shaping them into self-bending beams that can even curve around obstacles. Imagine that, sound that can bend around corners. Then, these metasurfaces direct these curved ultrasonic beams to cross paths at a very specific point, right where you, the listener, are located. Now for the clever bit. When these two ultrasonic beams meet, they interact in a non-linear way. If they have slightly different frequencies, say one is at 40,000 Hz and the other at 39,500 Hz, this interaction creates a brand new sound wave. And this new wave's frequency is the difference tonight between the two original ones. In our example, that's 500 Hz, which is perfectly audible to us humans. The most amazing part? This audible sound is only generated right there at that tiny intersection point. Step outside this enclave, even just a few centimeters away, and you hear practically nothing because the individual ultrasonic beams are still silent. Researchers have already shown this works for simple tones and are now generating a wider range of sounds from 125 Hz to 4,000 Hz, which is great for speech and music. This isn't just theory. Real-world progress is happening fast. Teams at places like Pennsylvania State University and Lawrence Livermore National Laboratory have made huge strides. They've built systems using two ultrasound transducers. Those are the things that create the ultrasound, paired with 3D-printed acoustic metasurfaces that emit these self-bending beams. In their experiments, they've used dummies with microphones in their ears to prove it. Sound was only picked up at that precise intersection point. Current prototypes can send sound about a meter away, at a volume similar to a normal conversation, around 60 decibels. And the belief is, by cranking up the intensity of the ultrasonic beams, they can increase both the distance and the volume. Okay, so private listening is cool, but where else could this tech go? The applications are mind-boggling. Imagine museum goers getting personalized audio guides without needing headphones, or library patrons listening to lessons without disturbing the silence. In your car, you could get navigation instructions while your passengers enjoy their own playlists, all in their own private sound bubbles. For augmented and virtual reality, this could mean incredibly immersive sound without clunky headsets. Think about secure communications, creating localized speech zones for private conversations in open offices or even military settings. Public announcements could be targeted to specific individuals in a crowd. Retail stores could offer unique audio ads to shoppers in particular aisles. It might even lead to super-targeted noise cancellation, creating quiet zones in noisy environments. And beyond audio, acoustic metasurfaces are showing promise in medical fields like ultrasound imaging, therapy, and even manipulating tiny particles. Now, as with any groundbreaking tech, there are hurdles. To get practical sound levels, the ultrasonic beams need to be quite intense, and we need to be sure about any long-term health effects. Achieving high-fidelity broadband audio like your fancy headphones is still a work in progress. Some current metasurface designs are a bit limited in the range of frequencies they can handle well. Power consumption and efficiency are also big factors for making these devices practical and portable. And, of course, making these precisely engineered surfaces cheaply and at scale is key for them to become mainstream, though 3D printing is looking like a good option here. Plus, the world isn't static. If you move, or an obstacle gets in the way, the system needs to be smart enough to track you and re-steer the sound beam. That's a tough engineering challenge, though some are looking at software and phased arrays to help with that. And finally, we need to see how these systems perform in different real-world conditions, like changes in temperature or air turbulence. But researchers are actively tackling these challenges. They're exploring new metasurface designs, like helical structures for broader frequency ranges and soft, flexible materials. They're developing better ways to model and optimize these systems, and looking into active metasurfaces that can be tuned or reconfigured electronically, offering even more flexibility. Acoustic metasurfaces are definitely moving beyond the lab and into the realm of real-world potential. The idea of private listening without headphones is just the tip of the iceberg. This technology could revolutionize how we experience sound in shared spaces, enable new forms of communication, and create incredibly immersive entertainment. The era of virtual headphones is dawning, and the soundtrack of our lives is about to get a whole lot more personal and precisely delivered. It's an exciting time for audio technology. What do you think about acoustic metasurfaces? Where would you use your virtual headphones? Let us know in the comments. That's all for this episode of Fun Facts Online. Don't forget to like, subscribe, and hit that notification bell so you don't miss our next dive into the amazing world of science. Thanks for listening.